All right, today we are diving into what is basically a quantum magic trick. It's a puzzle that hides one single perfect answer inside what looks like total, complete randomness.
So that's the big question, right? How do you do that? Well, this is the whole idea behind a really fascinating challenge in quantum computing. It's a technique for building a circuit that looks like pure chaotic noise, but it's actually this masterpiece of engineering designed to spit out one and only one specific answer. You see, on one hand, you have something called random circuit sampling. It just creates a chaotic mess of answers that's a huge headache for a classical computer to check. But on the other hand, you have these things called peaked circuits. Now, they also look like noise, but they've got a secret. They're sneakily designed to produce one specific answer with a super high probability, which means you can check if it's the right one almost instantly. So, how is this quantum sleight of hand actually done? Let's get into it.
Okay, so this isn't just random luck or anything like that. It is a brilliant four-step recipe. It's a whole method for building the puzzle, hiding the key inside, and yeah, completely fooling anyone who tries to reverse engineer it.
Think about it like you're building a perfect maze. First, you build the backbone. That's your complex random network of quantum gates. Then, you create a mirror of that maze, a path that leads you perfectly back out. Step 3 is the imprint, and this is where you weave the secret answer right into the very structure of that maze's path. And finally, you add the dimple, a clever disguise to hide the fact that there's any structure at all.
So the secret sauce to this whole thing is creating that perfect mirror. A way to absolutely guarantee you can get back to exactly where you started. Let's break down how that part works. All right, first up, we generate a really complex circuit. We'll just call it U. Now, this thing is a sequence of random quantum gates that just completely mixes up and entangles all the quantum bits, or qubits. Their fates are all tangled up together. If you were to just run this circuit by itself, the output would be nothing but pure, unpredictable noise.
Then, we do something incredibly clever. We take every single gate from our random circuit U, and we stick its exact mathematical inverse on the end, but in reverse order. This inverse circuit is called U-dagger, and it basically acts like a perfect mirror. So this combination creates what's called a mirror circuit. The first half, U, makes total chaos. The second half, U-dagger, perfectly undoes all of that chaos. And the result? Well, the circuit is guaranteed to always output the exact state it started in, which is the all-zero string. It's kind of like walking deep into a forest and then perfectly retracing your every step to get right back to the entrance.
But, getting an output of all zeros is boring. That's not what we want. We want our secret bit string. So the real question becomes, how do we embed that secret answer without just, tacking it on at the end where anybody could see it?
I mean, think about it. If we just added a few bit flip gates at the very end of the circuit to make our answer, well, anyone could just look at the code and immediately read the secret. That's not a very good magic trick, is it? Nope, we need a much more subtle way of doing things.
The technique they use to solve this is called polypropagation, and it's really cool. So imagine you want to change the last word of a sentence. Instead of just replacing it, what if you went back to the beginning and subtly changed a few letters in each word along the way, so that by the time you got to the end, the last word had changed as if by magic? That's what polypropagation does. It pushes the final answer backward through the circuit, changing the gates it passes through.
So as the instructions for our secret answer move backward, deeper into the circuit, they interact with every gate they pass. This process just subtly changes the circuit's internal wiring, and it effectively dissolves our secret message into the machine's own blueprint. The answer isn't tacked on at the end anymore. It's now an inseparable part of the circuit itself.
So at this point, our secret is hidden inside the circuit's parameters. But a really clever analyst might still spot that mirror-like structure, right? The first half looks random, and the second half, even though it's altered, it still mirrors the first half structure. That symmetry is a dead giveaway. We need one last trick up our sleeve.
Exactly. That underlying symmetry, even with all the scrambled parameters, is a huge clue. To make a real challenge, something that could fool even a supercomputer, we've got to break that symmetry. And this is the little dimple. It's a deliberate tiny flaw that gets introduced right at the center of the mirror, right at the seam between the circuit and its inverse. We take a small patch of gates at that midpoint, and we replace it with a completely different set of gates that does the exact same quantum operation, but just looks totally different.
So here it is, the full recipe in action. You've got chaos from the backbone, order from the mirror, a secret encoded with propagation, and then camouflage from the dimple. Each part has a critical job, and they all work together to create this puzzle that's perfectly ordered on the inside, but looks like total chaos on the outside.
So, we've got our completed puzzle. Now let's really dig into why this clever 4-step recipe creates a challenge that is so unbelievably difficult for even the most powerful classical computers to solve.
Well, for a classical supercomputer, that little dimple is basically a brick wall. It breaks the perfect symmetry that the computer could have used to simplify the whole problem, realizing that U-dagger and U just cancel each other out. Without that shortcut, it's forced to try and simulate the whole chaotic mess, which is an exponentially hard job. But a quantum computer? It doesn't need shortcuts. It just follows the instructions, and that path, no matter how disguised it is, leads it flawlessly to the one correct answer.
And get this, at just 36 qubits, simulating one of these circuits is already a massive, massive task for the world's best supercomputers. If you scale that up to just 50 or 60 qubits, it becomes classically impossible. Game over. You're not going to solve it in any reasonable amount of time.
This whole property gives the puzzle a special classification, QCMA hard. Okay, think of it like a locked treasure chest. Without the key, even the best locksmith in the world would find it nearly impossible to open. But if you have the key, you can open it up and check what's inside in seconds. The secret bit string we hid, that's the key.
So at the end of the day, this is way more than just a clever party trick. It's a perfect benchmark for quantum computers. If the machine doesn't find the one hidden answer, you know something is wrong. But maybe more importantly, it points toward a new era of cryptography, creating digital locks that are easy for the person with the key to use, but practically impossible for even another quantum computer to break without that key.
When you step back and look at the big picture, what this technique really shows is a profound level of control over the quantum world. It's the ability to embed predictable, deterministic order right inside what appears to be pure randomness. And that leaves us with a pretty fascinating final thought. If we can hide a single specific answer inside quantum chaos, what else could be hidden in there, just waiting for us to find it?